So last class we have discussed what type of reaction? Complex reaction. So last class I discussed. Have you read after that? Which reaction I have discussed? Consecutive reaction. So consecutive reaction, if you remember the scheme, it will be A to B and then B to C. And we have considered all are first order with respect to A and then first order with respect to B. So because there are two steps, first step rate constant K1, second step rate constant was K2. Similarly, I can consider today second type of complex reaction, that is parallel reaction. So parallel reaction, that means from a starting material you are getting two products. So this type of reaction frequently we will observe in organic reactions. Like if you do the nitration of toluene, you will get nitrotoluene as well as paranitrotoluene. Okay, that means you can get more than one product. So we can say parallel reaction or side reaction. Okay, so we have to know the concentration of C and concentration of D at a particular time. Our aim will be to know the concentration. So let's say both are unimolecular reaction with respect to starting material A or reactant A. So how I can write? So I can write, if I write with respect to product from C, then the concentration of C or rate with respect to C, if I write, that is dCdt. So dCdt will be K1 into concentration with respect to A. So I can write this dCdt as well as I can write with respect to compound A. So that I will be writing in the next step. So similarly for second product D, I can write d dt. It will be K1 into A. So this I have written the rate equation in terms of product formation. Now if I want to write the rate equation in terms of the reactant A, so I will write minus dA dt. So A is consumed by two different reactions. How I can write? Sake of simplicity, I can say it is a summation of rate constant. It is just like simple summation because in two different steps or two different reactions are going on with rate constant K1 and K2. So the A, its rate of disappearance, it will be simple summation of K1 into A plus K2 into A. That's why I have written in summation of two rate constants in a bracket into A. Okay, because in two different steps A is consumed. So if I want to write in terms of product, so for product C, I will have the rate equation K1 into A. For product D, the rate equation will be K1 into, it will be K2 into A. Okay, because K1 is the rate constant for product formation C, K2 is the rate constant. So these are small k. Always you remember rate constant means it will be small k. And equilibrium constant is capital K. So now if I want to write the rate equation in terms of the reactant, then it will be minus dA dt, and you will have simple summation of two rate constant into A. So you know, for a unimolecular reaction or first order rate equation, how you can write at a particular time the concentration of A, it will be A naught e to the power minus K T. This is a general. After solving the rate equation for a unimolecular rate equation, okay, where rate constant is K. So if I have this type of reaction A to product B, then at time T the concentration of A will be initial concentration of A, that is A naught multiplied by e to the power minus KT. Now same way you can think that now A is converted into, in my parallel reaction scheme, A is converted into two product C plus D. That means this rate equation. So if I solve it, do the integration, then what will be my A? A is the concentration of the compound starting material after time T. Simply you can write, after solving it, you can see it will be nothing but K1 plus K2 into T. Okay, so this is like a first order reaction. So after solution, after integrating, you will get the time T, the unreacted or the amount A left in the reaction vessel, its concentration will be initial concentration multiplied by minus K1 plus K2 e to the power minus K1 plus K2 into T. Now my next question is, what will be C and what will be D? That means what will be the concentration of the two products, product C and product D. So rate equation already I have written for C product formation is dC dt K1 into A. Now I can substitute in place of A. What I can write? In place of A, I can write it is K1 A naught, in bracket also or without bracket also you can put, e to the power minus K1 plus K2, their summation, into T. So it has gone out of the screen, so I will make it little smaller, minus K1 K2 into T. So similarly, if I ask what is the rate equation for product D, then change of concentration of D, I can write K2 into A naught e to the power minus K1 plus K2 into T. So I have two different rate equation, only difference is in one place it is K1, another place it is K2. Okay, so if I solve these two differential equation, or if I do the integration, I will get the concentration of D and C and D. Okay, so the A, that one already I have told that unreacted A, it will be A to the power minus E K1 plus K2T. Now my next aim is to get the concentration of the two product at a particular time T, any arbitrary time T. It can be obtained by integrating the rate equation 1. If I integrate rate equation 1, I will get the concentration of C. If I integrate the rate equation 2, then I will get the concentration of D. So I will show for one, other one you can easily do it. So from equation 1, I can say dc dt, I am writing once again K1 A naught e to the power minus K1 plus K2 into T. So now dc will be, so K1 A naught e to the power minus K1 K2 T dt. Now if I integrate, so two constant term I have kept out the integration sign. One is K1 and another is the initial concentration A naught, that is a constant term. Okay, so what will be the limit now? Lower limit when time equal to t equal to 0, what is the concentration of C when reaction started?
0. 0.
0. And upper limit will be when time is t, then you will have concentration C. So I can write it will be C, and in this case K1 A naught and then e to the power minus K1 plus K2 T by the rate constant term, that will be constant term. So I am taking out of the bracket integration limit t equal to 0, t equal to t. Okay, fine. If I do any mistake, please indicate or suggest. So now you put time, one time it is 0, one time it is t. So K1 A naught minus K1, all are small k, K2, one case it will be minus K1 upper limit when you will put t minus e to the power 0. So e to the power 0 is 1. Directly I put t equal to 0. So t equal to 0 means it will come out to be e to the power 0. So e to the power 0 is 1. So what I am doing, I am just rearranging so that I have 1 that I have put in the initial, and then I put the e to the power minus K1 plus K2t, then minus K1 plus K2, it will become plus K1 plus K2. So the concentration of C you will be knowing by this equation. So similarly, if I solve for D, it will be, where will be the difference? In place of K1, you will have K2. Other than that, all the terms are same. This is simple solution. Other terms will be same. Okay. So two product, if you have following the first order reaction or unimolecular reaction, then C and D, their concentration at a particular time you can calculate by these two equations, and the amount of A that remains unreacted, that will be simple e to the power minus first order reaction. How you can write? Same way you will write, only thing. Okay. So at a particular time, any time t, if I measure the concentration of C and D, two product you have, if you take out from the reaction mixture and you just make their ratio, how much C and how much D has formed, what will be their ratio? Equation, these two big equation, if you see, if you make ratio, that is equation 3 divided by equation 4, that is the concentration ratio of product C and D. You will see all the terms will cancel out except
K1 and K1 by K2.
K1 and K2. Okay, that means their ratio is their rate constant ratio. So anytime it will be constant. So if it is for 5 minutes, if you make their ratio, product ratio, you will see that will be ratio of their rate constant. 10 minutes, the product whatever C and D has formed, if you measure it and you make the ratio, you will see the ratio will remain constant because that is K1 by K2. So this type of reaction is known as, have you heard kinetically controlled? Kinetically
Yes, sir.
controlled. And another term you might have heard, thermodynamically controlled. What does it mean? So kinetically controlled means when rate equation or product formation is governed by the rate constant. How first two products are formed. So K1 is and K2, these terms are depending on, I already discussed in last today's lecture only. They are depending on the collisions, how they are colliding and giving you the product. So K1, K2, that governed by the time, how fast or how rapidly products are formed. So if K1 is larger, then concentration of product C will be larger. If K2 is larger, then the concentration of D will be larger. So kinetically controlled reactions is completely governed by the rate constant. So higher is the rate constant, higher will be the amount of product. Another concept is thermodynamically controlled. So kinetically controlled, that is controlled by rate equation. Thermodynamically controlled when there is a reversibility. So a reaction, I will erase this equation. Okay. So this solution I will erase now. Thermodynamical, that rate equation I will not derive because it will be little bit complex, but you should know the concept. When you have the reactions are reversible, so many reactions, those are reversible in nature. So industrial processes as well as any laboratory based reactions also, those are having reversibility. When rate constant is very large, we can say reaction is irreversible, but that will be the extreme case. But more or less all reactions are reversible. So as I have shown just now, the reaction, what I have shown, the reaction A is giving you product C and D. I can think that the product, whatever C has formed, that can come back to A. Similarly, D can also come back to A. So I can have another rate constant. One is K minus 1. That is the backward reaction, which is product to reactant C to A. And another backward reaction is D to A. So that is K minus 2. So how many equations you will have now 4 equations. 2 are forward reactions and 2 are due to backward reaction. So 4 rate constant I can associate with this one. So a reaction schematically if I show, then let's say this is your energy scale. A is there, it can go to the C. Let's say this is A, it is passing into C. Similarly, A can pass into D. So A can move to C and A can move into D. So there are 2 terms. One is activation energy. I can say this is the 1 product formation C, and this is the activation energy 2, that is the starting material A converted into product D. Now let me first you say which one is more suitable or rate will be higher, product formation C or product formation D.
So D is reactant now.
No, A is reactant only. So I have put A in the middle and
So,
2 different. So I have plotted in different way. So I could have plotted A on the left side. So different book they represent differently.
सर
Someone
कोई भी हो सकता है, अगर
so
थर्मोडायनामिक्स से देखेंगे तो कोई भी हो सकता है, या काइनेटिक्स से देखेंगे तो कोई और होगा.
one book they can show A is converted into C, one is D, like that I can show. Okay, from A to C and D, but I have shown in this way for better visualization. So A at the middle, that is your starting material, converted into product C and D. So kinetically controlled means which one will have higher rate, which will be converted
सर
faster.
सर डी का फॉर्मेशन जल्दी होगा
Q.
क्योंकि ये इसका कम है, एक्टिवेशन कम है, तो इसका रेट ज़्यादा होगा.
Yes, so kinetically controlled reactions are governed by the activation energy. That you remember that lower is the activation energy, A can easily pass to the product D as compared to the other way because it is having higher barrier. Now, if you see the final energy, which one is more, which is lower, C or D, according to my figure?
C.
C. That means thermodynamics says the product energy, it is not interested with the energy of the transition state. Thermodynamics is much more associated, or it is much more useful to explain the stability in terms of product's energy. So product energy, if you see, D is at higher level, C at lower level. So the difference between A and C, their energy difference, and A and D, their energy lower in energy. So thermodynamically, product C will be much more stable. So I told just now the reversibility of the reaction. So what may happen if I show in the scheme the D, which may go back to A by the backward reaction, and A can move into C in the forward reaction. So what can happen? If you keep the reaction for very longer period, then the reversible reaction will start to occur. The product CD what has formed, its barrier height is less because activation energy is less, so it can easily go back to A, and A further gives you the more stable product C. That means already product had formed. So you have put a reaction. After 1 hour, you will see the amount of D is much larger than the C because reaction is governed by the rate constant. Since activation energy for the D formation E act 2 that is lower than the E act 1, after 1 hour I might get much more quantity of D in the reaction mixture as compared to C because activation energy is less. But if you keep the same reaction for 24 hours, there you might see most of the product is now C because due to the reversibility of the reaction, the product whatever D has formed that has gone back to the starting material A following the backward rate constant K minus 2 and then A converted into the more stable product C. That means this reaction is controlled by the thermodynamics. So product C formation is thermodynamically controlled and product D is controlled by the kinetics because rate constant is higher for product D formation. So time is very important factor here. So shorter duration, which product you see it has formed, that means that product is kinetically controlled. And for longer duration of reaction, the product what you see is you have in the reaction mixture that is thermodynamically controlled. So according to this scheme, I can say C is thermodynamically controlled product and D is kinetically controlled product. Okay, so thermodynamically controlled product, for that case the concentration of two products will be, their ratio will be, if it is kinetically controlled then it will be K1 by K2, and if it is thermodynamically controlled product then you know A2C and A2D. What is capital K?
Equilibrium constant.
Equilibrium constant. So capital K is K equilibrium. So equilibrium constant you will write as concentration of product by concentration of reactants. So that is the first equilibrium, capital K equilibrium 1, and for the second step I can write K equilibrium 2. So K equilibrium 2 will be D by A, concentration of D by concentration of A. So now if you make the ratio C divided by D, what you will find? It is a ratio of K equilibrium 1 divided by K equilibrium 2. So what you are seeing, you have seen if it is thermodynamically controlled, then the product ratio will be the ratio of their rate constant. So these are the ratio of rate constant. So that is known as kinetically controlled. And if it is thermodynamically controlled, then the ratio of the product will be ratio of equilibrium constant. Then I can say that is thermodynamically controlled. Okay, so the equations, the derivation for the backward reaction I have not shown, it will become little larger. So you can see in the PDF the backward reaction rate constant also you can easily get it by forming the suitable rate equation, and then there after that you have to solve by integrating the differential equation. Okay, so the concept is important. What is thermodynamically controlled and what is kinetically controlled? Any doubt?
No, sir.
Okay, so one PDF usually we are giving in the last semester to the BTech students, last or previous year when I have taken. So this PDF is little different from the PDF what is shared. Both are equally mentioned. Okay, so you can see this part from the previous year PDF. That also I will share in the folder file section, you can see. So if you don't have any question, then I can take the attendance and I can end today's class. You have any question? Do you have any question? No, na? Okay, then let me take today's attendance. Okay, so anywhere, anytime, if you have doubt, please ask me. Or in previous notes also, previous class also, if you have any doubt, you can ask me anytime. So I'll stop
Thank
it.
you.
Welcome. Okay, so we'll meet next class with the chain reaction. Last topic in the complex reactions section. After that, I will move into catalysis part. Okay, bye. See you on next week. So please stop the parallel classes if you have started anything.